Okay, so what we're going to do now is we're going to focus on the two other types of uh, transformations, which has to do with vertical and horizontal stretch and shrinking. So let's talk about vertical stretching and shrinking. So if you think about it, when we're talking about this, when we're talking about vertical stretching and shrinking, we're kind of trying to vertically, that means either push down or move up a function, which if you notice, if I'm vertically stretching or shrinking, which values does that affect? Once again, that affects my y values. So we would say, look, if you have the graph, y equals to c times f of x. Now notice how I'm multiplying my c to y. So then the question is, how do I know if it's shrinking and how do I know if it's stretching? Well, it all depends on the value of c. So if c is greater than 1, which then what is that going to do? If c is a number that's greater than 1, then this y value is going to get larger, which means it's going to stretch it. So this means stretch the graph of y equals f of x vertically by a factor of c. So what we're basically doing is this is the y values are being multiplied. Right, so that's literally what we're doing. So we're literally multiplying all of our y values by c, and the x values are staying unchanged. So when will I get a compression? It's when c makes y become a smaller number, and that's when we have a fraction, or when it's between 0 and 1, right, where we have a fraction between 0 and 1. So if c is greater than 0, less than 1, then that's going to cause it to shrink. So this means we will be shrinking. So you shrink the graph of y equals to f of x vertically by a factor of c. So once again, it's the y values that we care about. So these are the y values. So just keep that in mind. So let's look at an example, or our next example, which is the fourth one in this section. We're going to say sketch f of x equals to 1/2 times negative x minus 1. Okay, so once again, notice how if I have something other than just a positive 1 in front of the x, I want to write this in factored form. If you remember in the notes on the first part, when we had negatives, we said, look, we don't want the x to have a negative. We want it to be just a positive, and more importantly, we want it to just have a 1 in front of it. So I'm going to factor out a negative, and we're going to use transformations. So let's go step by step. What is it that I have? This 1/2, notice how it's on the outside. See, if it was on the inside, like if the 1/2 was tied to the x, that would be a different story. But since the 1/2 is outside, this is saying, look, whatever the y value is, we're cutting it in half. So this is a vertical compression. The minus is what? If you think about it, the minus is in front of the x. That's a reflection about the y-axis, and then this -1 is saying shifted 1 to the right. So if you remember, we always want to do reflections first, and then I always leave my vertical and horizontal transformations to the end. So shifting things left and right, up, down, I always leave that for the end. So what's the parent function we're going to start off with? Well, it's the square root, isn't it? So I'm going to say we're going to start off with f of x equals to square root of x. I'm going to graph that 0, 0, 1, 1, 4, 2. And then what am I going to do? I'm going to reflect it because of that minus. So it'll be f of x square root of negative x, which literally grabs the graph and reflects it about the y-axis. So it's going to look like that. Okay, good. And then I'm going to take care of the horizontal compression. So f of x equals to 1/2 square root of negative x, which, what is this saying? Just grab all your y values and cut them in half. So this has a y value of 0, which half of 0 is still 0. Now notice the x values are not being affected. It's just the y values. At -1, this has a y value of 1, which means it'll be half now, because I'm cutting that y value in half. And at x equals 4, this has a y value of 2, and if I cut that in half, it'll be 1. So, and hopefully you could see why it's called a compression. If you compare this to that, it looks like I pushed down, I compressed it to get it to that. Okay, now the last thing I need to do is to basically take care of that this minus 1, which means shift everything 1 to the right. So since I'm running out of space, I'm just going to grab this same graph and move everything 1 to the right. So this point will go over there. This point will be now where? Instead of -1 1/2, it'll be at 0 1/2. This point, instead of 4 1, it'll now be where? At 3 1. So it kind of looks like that. So this is my final, so that is my final graph. Okay, so once again, I use transformations to do this. So now let's talk about horizontal stretching and compressing, which means if I'm stretching and compressing horizontally, it's my x values that are being affected. So notice how this c was multiplied to the y values. Hopefully you're saying that to yourself, well then if I'm horizontally stretching and shrinking, then I would have to multiply c to the x values, because that's what's going to get me to move things horizontally. And that's exactly what's going to happen. So let's take a look at horizontal stretching and shrinking. So we're going to say to graph y equals to f times cx. Okay, so here's where we kind of have to be careful about this, because remember the vertical stretch and shrinking for c, the number just told you whatever it was. If it was greater than 1, we stretch. If it was between 0 and 1, we shrink. This one is kind of backwards. It's the opposite. So think of it this way. If c is greater than 1, then we're shrink the graph of y equals to f of x horizontally by a factor of 1 over c. So in other words, here's what we're saying. Whatever this is, to stretch or shrink, we're going to grab all the x values and we're going to multiply it by 1 over c. So do you guys see the difference? Hopefully you do. For the vertical stretch and compression coming back up here, we multiplied all the y values by c. For the horizontal, we multiply all the y values by 1 over, or x values, not the y values. We multiply all the x values by 1 over c, which is why it causes it to be a shrink. So this basically is saying multiply all x values. Okay? So then if c is between 0 and 1, then this becomes a stretch. So then we stretch the graph of y equals to f of x horizontally by a factor of 1 over c. Okay, so once again, these are the x values we're multiplying to, right? As you could see, it's paired with the x, okay? So let's move on to our next example where we'll put this to use. So for example 5, we're going to say sketch the graph of f of x equals to 2x plus 4 squared. Now once again, see, if I see anything with the x other than just the 1x, I want to factor this. Remember with the negative I factored that. Same thing here. if there's something other than just the 1x, I have to write this in factored form. Here's the reason. If you look at this and I ask you, hey guys, this has a horizontal, not a horizontal stretch. It has a, in this case, by looking at that +4, this is telling me that I have a horizontal shift. And I would ask you, hey, what is this saying? What's the +4 saying? And if you don't rewrite this, you will by accident say that this is saying the graph shifts 4 units to the left. But that's not true. Because of this 2, it throws things off. So whenever you have something other than just an x, we have to rewrite this in factored form. So I'm going to factor out the 2 from in here. And obviously I'm not going to move it all the way outside. I'm just going to leave it like this. It'll be x plus 2. Now hopefully you see what the problem was. We're not really shifting this 4 units to the left. We're actually shifting it what? Notice how it's x plus 2 because there's my 1x. This is when we see the true shift, which is 2 units to the left. So let's look at this. This 2 is saying do what? Multiply all your x values by 1/2 because that's my horizontal compression. This 2 is saying shift everything 2 units to the left. So the parent graph I'm going to start off with, notice how this is a quadratic, it's squared. So I'm going to start off with f of x equals to x squared, which 0, 0, 1, 1, negative 1, 1. This is how it looks. So then I'm going to take care of my compression, horizontal. So remember, what is this 2 saying? You think in terms of its reciprocal. So this is saying grab all the x values of the points and multiply them by 1/2. So over here, this has an x value of 0. 0 times 1/2 is still 0. Now what you're going to notice is the y values don't change, but the x values change because of this. So for this point, the y value is going to stay 1, but the x value is 1, and when I multiply the x value by 1, I get half. So it'll be 1/2 and 1. And then this one has an x value of negative 1, so if I grab negative 1 and multiply it by 1/2, it'll give me negative 1/2 and 1. And when I graph this, now notice how when I compare this to that, it looks like I compressed it horizontally, and that's where it gets the name horizontal compression. So the last thing I need to do is what? Shift this graph 2 units to the left. So I'll get my last graph, which is f of x equals to 2 times x plus 2 squared. So 0, 0 will now be where? Negative 2, 0. And then 1/2, 1 will now be where? Negative 3/2, 1. And then negative 1/2, 1 will be right there, which is negative 5/2, 1. And there you have it. And I just graphed my function using transformation. So hopefully you see why transformations is the better way to graph this, because trying to graph this all at once might not be as simple. But if I start with the basic one and provide the appropriate transformations, then I get to where I want to get to. And be ready for the test. I will definitely ask you to use transformations to do so. Okay, so let's now move on to even and odd functions, which this is going to be the last thing we talk about. So now we're only going to talk about how to check if functions are even and odd, and then after that we will later on figure out what graphical representations even and odd functions have. Okay, so we would say let f be a function. Then we would say that f is even if f of negative x equals to f of x. So let's be careful what this is saying. I have f as a function. So if f is an even function, here's what this claim is. It's saying, look, if you grab x and you replace it with negative x, and then you simplify it, you should get back the original function. If you get back the original function, then it's even. Okay? And then we would say f is odd if f of negative x, so now what are we doing? We're still replacing our variable with negative x, and when you simplify it, you get the exact opposite of what you started off with, and that's odd. So if you replace x with negative x and you don't get the same thing or the exact opposite, then guess what? It's neither. Okay? So this is a simple test when you're asked to check to see if something is even or odd. Just plug in negative x into the function and then simplify it. And then compare it to the original function. Is it the same? If it is, it's even. Is it the opposite? If it is, it's odd. So let's look at our last example, and then this will wrap up this section. So if I would say determine whether each function is even, odd, or neither. Now, when I work this out, there's 3 of them I want you to try. Maybe you want to watch the first one along with me, and then you could pause the video and try the next 2 out on your own, and then we can talk about it. And then you could press play and see what your answers, how your answers compare to mine. So let's look at part A. I want to see if this function is even or odd or neither. So instead of f of x, what am I going to do? I'm going to replace x with negative x. So how's that going to change this equation? All it's going to do is x is going to become negative x cubed, right? Because I'm replacing x with negative x plus negative x. And now I'm going to simplify this. And if I simplify this, what's negative x cubed? So negative x times negative x times negative x ends up being just negative x cubed, like that. And then plus minus x, which makes it negative x. And if you compare this to the original, what do you notice? It's the exact opposite. Better yet, if I factor out a negative from this, I get, which notice how this is the original function, except I'm multiplying a negative to it. Which means, what do we just show? This is the same thing as negative f of x. And if that's the case, right, because that's f of x, that's the negative. If that's the case, this is odd. Okay? So maybe you might want to pause this video and try these 2 out on your own, and then press play. So let's move on to the second one. So to check to see if this is even, odd, or neither, I'm going to replace x with negative x. And, well, this is a constant. There's nothing for me to replace. It'll be 7 minus, this x is going to become negative x to the 6th. And then negative x to the power of 6, this becomes positive x to the 6th. So it'll be 7 minus, this minus is that. And that minus becomes positive x to the 6th. And then when I'm done, when I compare this to that, what do I notice? F of negative x, when I simplified it, I got the same thing back as f of x, which makes this even. Okay? Lastly, let's try this one out. F of negative x equals to 3 times negative x minus negative x cubed. And what do I get here? 3 times negative x is minus 3x. Negative x cubed is, negative x cubed will still be negative x cubed, but with that extra negative makes it a plus x cubed. And when I compare this to that, I notice that they are exact opposites. In fact, if I factor out a negative, I get 3x minus x cubed, which this is just negative f of x, which makes it odd. Okay? And by the way, not all functions are even or odd, right? Obviously there are neither. We just didn't do an example where there is a neither. But if you want to see a quick one, or if you want to try one out, here's one that's definitely neither. Try this one out. Try to check to see if this is even, odd, or neither, and you'll see that it ends up being a neither. Okay, so this takes care of this section. So as always, if you have questions, don't hesitate to email me or ask me when I see you guys in person.